Hi everyone, this is Kwan here. We've been talking about Bayes' theorem a bit, and I just kind of want to show you how it comes about. It's a theorem for a reason because its theorem is derived from the regular definition of conditional probability. Normally, we like to think of probability as just plug and chug, but we don't understand the full ramifications of it as Bayes did. So, what am I talking about when I'm talking about conditional property probability? Normally, in logic, we know what a conditional is. A conditional is a statement of the form P arrow Q, commonly read as P implies Q, or if P then Q, or Q only if P. Um, and in probabilistic terms, we want to say Q given P. So with that in mind, we'll start. The definition of conditional probability is this. I'm going to use 1. Um, and I'm going to go probability of Q. I already messed up. Sorry. This is conditional probability. The probability of Q given. I'm going to use this line, this bar here. Is given equals the probability of P, this caret here, and Q. I like to use the caret because it's an and. It kind of like houses everything underneath the roof. So probability of P and Q over the probability of what is given. So if P is given, then probability of P. Okay. Line 2. Natural consequence of this is this. Once again, we stick with what we're trying to define here. Q given P equals, we're going to stick with that here, the same thing. Only have P or and Q. Now, I'm going to change this a little bit. I'm going to say that this is going to be the probability of P and Q, or P and not Q. Now, why do I say this, or why is this the case? I'm going to write out the equivalent first, the equivalent theorem in sentential logic, and it's going to be P if and only if P and Q, or P and not Q. So intuitively, this means P is identical, or P is equivalent to, or P is defined as P happening with Q, or P happening without Q. Suppose I'm going to have coffee. I can either have my coffee with cream or coffee with not cream. Does that sound right? Or no cream. So it's either one of them is going to happen. And I can either have cream or not cream. So intuitively, that's what it is. And of course, it can be proven. It is a regular theorem. It's one of the patterns you might see in logical thinking. So the proof for it, in short, will be we want to prove it both ways. We want to prove the arrow going this way, and we want to prove the arrow going that way. And I'll show you one way first. P implies P and Q, or, oops, actually this is an and. See, little like errors like that. P and not Q. Okay, so how do I do this here? What I'm going to do is I'm going to P is the assumption, and I want to, by reductio ad absurdum, I want to assume the opposite. I'll bracket this out here. P and Q, or P and not Q. So by De Morgan's theorem, I come up with not the case P and Q. The OR becomes an and driving in this negation, I get P and not Q. And because these are still in the bracket, they don't change. I can further apply De Morgan's theorem and do this. Well, or I can split them apart. I'm just going to do them in one big step. Using De Morgan's theorem, I can come up with not P or Q. Because the and becomes an or, I'm going to actually split them up, and then the next line I'm going to have not P or not Q. Okay. So if I have the statement, either I have not P or not, this would be not Q, which becomes Q anyway. Let's just say that. Don't want to go through another step. So P and this line will give me not Q, and P and this line will give me Q. I have a contradiction there. So the opposite of this, which is this, holds. So I have just proven that P implies P and Q, or P and not Q. Okay, very nice. How about the other way? Well, I guess we could do it the other way too, but just for variety's sake, I'm just going to do a truth table for that. And actually, sometimes these are even faster. You don't have to think. So because I want to prove it the other way, I'm just going to write it this way. Just imagine this arrow flipped. P and Q, or P and not Q. This whole thing here implies P. So I'm just going to add in my values. I know P is 1100, Q is 1010, 1100, and for not Q, I'm just going to use the opposite of Q, right? If this is 1, this is going to be 0, 0, 1, 0, 1. And of course, P here retains the same value, 1100. So for P and Q, the rule is if P is true and Q is true, then P and Q is true. And none of these hold. 1, 0 is 0, 1, 1 is 1, 0, and 0. So I'm working with these two values here to come up with this value here. So I look at an OR statement only requires one side to be true for the OR statement to be true. So 1, 0, 1 here, and 1, and I have neither true on both sides. And oh, look, all of a sudden, what do we have here? We have values, identical values, 1100 and 1100 for this whole statement here. So in actual fact, we've proven the biconditional. But since we're only doing it one way, we can just use this value and this value to find the value of the arrow. 1, 1, 1, 1. So we know they are equivalent, actually. So we've shown that to be equivalent. That's why this whole entire thing can be substituted salva veritate for that. Okay, so this is the theorem we use. Third thing. The third one, of course, now we want to do arithmetic because the ORs don't tell us what to do. Well, they do. And the ANDs don't tell us what they do, but they do, right? Because we have general disjunction and general conjunction rules for probability. So we can rewrite it. Probability of Q given P equals probability of P and Q. And the general disjunction rule, if you remember, for probability, if it's an OR, you add. So this becomes a plus. So it becomes a probability of P and Q plus the probability of P not Q. Okay, so now this is where it gets tricky. I'm going to uh, rewrite over here, I guess. Uh, the whole this definition of conditional probability here. And if you remember your basic algebra, probability of Q given P equals, because it's algebra, because we still have an equal sign there, we're still doing algebra or mathematics or arithmetic, probability of P and Q over probability of P. So there's an equal sign here, and basically this is a divide sign. So I don't know if you are guessing correctly or not, but what we can do is now we can do, because this is a divide sign, we just take this. Eventually this comes up here, right? Because, well, we can add stuff to both sides, but we can just do Singapore quick style math here and skip that step. So we end up with the probability of P times probability of Q given P equals probability of P and Q. What does this mean for us here? Well, it means that this just changed over here, because now we can actually substitute. For example, here we actually do it turns out that we can rewrite 4 as Bayes' theorem, which becomes probability of Q, okay, given P equals one big thing here. It becomes probability of Q times probability of P given Q over, well, should I let you guys, or, well, I guess I'll fill in the blank here. It becomes probability of Q and because it's general disjunction rule here, thus oh gosh, hard to switch between logic and close bracket and open bracket again, parentheses, probability not Q times probability of P given not Q, and parentheses, close parentheses here. So we see how we arrived at ingeniously. It's not just something out of thin air and that's something that you should accept on face value, but if people do ask you about Bayes' theorem now, you can like show them that you know how Bayes' theorem comes about. And that's all I have for you. So happy gambling, I guess. I'll see you guys, if not before the summer, in the fall. Bye-bye.